This problem gives us a chance to apply Rolle's theorem. We have this function, and it asks why it has exactly 1, negative 0. So when it says exactly 1, we really have to show two things. We have to show why it has at least 1 and why it has no more than 1. So for the first part, whether or not it has 1, probably we can use the intermediate value theorem. If we look at this function, we can see that if we plug in a negative number, then this will be positive, and a negative number squared will be positive, so a positive divided by a positive will be positive. But then this number, since if you cube a negative, then that's still going to be negative. So initially, if we plug in a number that's just slightly negative, this won't be too big, and the other two numbers will be positive, so we should get positive values. And then as we make the number more and more negative, this term, we're going to take 4 and divide it by bigger and bigger positive numbers. That's going to fade away to 0. And then if the number is really, really negative, then cubing it will make it super negative. So that should overwhelm it and pull us across the x-axis. Let's just check a few values. If we try negative 1 here, we get negative 1 plus 4 over negative 1 squared would be 4 over 1. That's 4 plus 7. So we get 10. We're above the x-axis. But if we go further, let's say we go to negative 2, then we'll have negative 8, and negative 2 squared is 4, 4 over 4 is 1, plus 7. Oh, we actually hit 0, so we're on the x-axis there. So we know it has at least one 0 because we just found one. I didn't expect that to happen. I was thinking if we went far enough, like let's say it would go to negative 3, we'd have negative 27 plus 4 over 9 plus 7. You can see this number is less than 8, so if you subtract negative 27, that's going to be less than negative 19, which is definitely less than 0. So we know, even if we hadn't stumbled on the exact value of the 0, here's negative 1, and here's negative 3. At negative 1 we were at 10, at negative 3 we were below the x-axis, and since it's a continuous function, by the intermediate value theorem, it would have to cross the x-axis at some point. It just so happens we stumbled onto that place, which was negative 2. So we've got that handled. We know that there's at least one negative 0 because we found it, or we can infer its existence from the intermediate value theorem if we hadn't found it. How are we going to show that it doesn't have more than one? So let's say it has two zeros. We found one at negative 2. Let's say there's another one maybe over here. Since our function is continuous and differentiable on this interval, then Rolle's theorem says that there must be some place in between where the derivative is 0. So let's check out the derivative of this function. We have f prime of x. The derivative of x cubed would be 3x squared. This is really 4x to the negative 2, and so that derivative is going to be negative 8x to the negative 3, and the derivative of 7 is 0. Now, I want to see if there's some place where the derivative is equal to 0. So what I should do probably is combine these into a single function. I have a single fraction. I have 3x squared minus 8 over x cubed. If I multiply this top and bottom by x cubed, we'll have a common denominator. We'll get 3x to the 5th minus 8 over x cubed equals 0. Now the only way this fraction could be equal to 0 is if the denominator, or the numerator, is equal to 0, sorry. And that would say that x to the 5th is 8 over 3. Well, since this is an odd root, the only solution to this problem would be a positive number, right? So because you couldn't take a negative number and raise it to the 5th power and get a positive number. So the only solutions of this that are real numbers are positive. In fact, I guess the only real solution is the 5th root of 8/3. So there's never a place over here where the derivative is 0. So over here the derivative is always greater than 0. If there was another 0 by Rolle's theorem, then there would be a place where the derivative was 0, and that's a contradiction. So so if there was another negative 0, it would contradict Rolle's theorem. So we know that we found one and there can't be another, which takes care of that problem. Let's look at another problem where we can use Rolle's theorem. We have this function and we want to show that it has exactly 1, 0. That means we're going to have to show two things. We're going to have to show that it has at least 1, 0. And then we're going to have to show that it's impossible for it to have more than 1. So if it can't have more than 1, it can't have 2. So show that R can't have 2 zeros. That's going to be our two-step approach to this function. Now, looking at this function R of theta, and see that it's equal to 2 theta minus the cosine squared of theta plus root 2. So this function, let's see, that's going to be a positive, and this is always going to be subtracting something, so that's going to be negative, and then this will be positive or negative. The thing is, this cosine squared always stays pretty much under control, right? Since cosine is definitely between negative 1 and 1, cosine squared is between 0 and 1, so we're never subtracting more than 1 on this function. So what I can see is as we go backwards, if theta is a really negative number, this guy will be super negative, and it will overwhelm whatever this can do, right? On the other hand, if we go forward, theta will be 2 theta will be really positive, and it will carry this to the positive side. So for example, if I plug in 0, R of 0 is going to be 0 minus the cosine squared of 0 plus the square root of 2. Well, the cosine of 0 is 1, so cosine squared is 1, so we get negative 1 plus root 2. Root 2 is more than 1, it's about 1.4, so that's greater than 0. On the other hand, if I just go back a little ways, let me try negative 2. If I go back to negative 2, 2 times negative 2 would be negative 4, and we have the cosine squared of negative 4, and then we have the square root of 2. Well, this is going to be, let's see, if we don't take anything away, so subtracting cosine squared will be removing something from this thing, so if I don't remove that cosine squared, then I'll have a number that's slightly bigger, but even that number is less than 0. Since this is only about 1.4, if you take away 4, that's definitely less than 0. So we know on our function that at 0 it's above the x-axis, but at negative 2 it's below the x-axis. So somewhere in between there, because it's a continuous function, by the intermediate value theorem, it's going to have to cross through the x-axis. It's possible that it crosses through maybe several times, but we know it has to cross through at least once by the intermediate value theorem. So we know by the intermediate value theorem that it definitely has at least 1 0. Now let's suppose that it has 2 zeros. Well, if it had 2 zeros, then there would have to be some place in between, according to Rolle's theorem. This is a differentiable function. There'd have to be some place in between where the derivative was equal to 0. Let's check out the derivative of this function. So R of theta is 2 theta minus the cosine squared of theta plus the square root of 2. So dr d theta is going to be 2 minus 2 times the cosine of theta times the derivative of the cosine would be negative sine theta, and the derivative of square root of 2 is 0. So this is 2 plus 2 times the sine theta times the cosine of theta. 2 sine theta cosine theta is actually a double angle identity. 2 sine theta cosine theta is equal to the sine of 2 theta. And here's where I notice something. This is always positive because the sine of 2 theta is always between negative 1 and 1. Right? The sine of any angle is between negative 1 and 1. So if we have a number between negative 1 and 1 and we add 2 to it, see, if I add 2 to all sides of this inequality, 2 plus negative 1 would be 1, is less than or equal to 2 plus the sine of 2 theta, and 2 plus 1 would be 3. So our derivative here, dr d theta, must always be between 1 and 3. That means the derivative is never 0. So that means it's impossible for it to have two zeros, because by Rolle's theorem the derivative would have to be equal to 0. So by Rolle's theorem it can't have two zeros. And we're done.